Hello everyone, my name is Martin Alain. I'm a postdoctoral researcher in the Distance project in Trinity College Dublin, where I'm currently working on light field imaging. And in this video, I'm going to present my paper entitled A Spatio-Angular Binary Descriptor for Fast Light Field Interview Matching. So this is the outline of this presentation. And I will now start by introducing the main concept of light field imaging and related work. So in this work, we consider the two parallel planes parameterization of the 4D light fields, where we can consider the light field as a collection of 2D images arranged on a regular 2D grid. Each image corresponds to a different viewpoint of the scene and is indexed by U and V, which correspond to the 2D spatial dimensions. And we index the different viewpoints with S and T, which corresponds to the 2D angular dimension. One of the landmark applications of light fields is the possibility to estimate the disparity or depth maps of the scene. And this is one of the target applications for the binary descriptor that we propose. And there are multiple ways to achieve this, which are listed here. But the descriptor proposed in this work is mostly relevant to methods which directly estimate correspondences between the light field views, also called interview matching. There are a lot of descriptors that have been proposed to improve the speed and accuracy of inter-image matching applications, such as optical flow. But in this presentation, I'm only focusing on the three descriptors listed here. And it was shown in the Boom paper cited here that they outperform most of existing descriptors. So these are also the descriptors that we used for comparison in our experiments. And the common insight for all these descriptors is that they are based on a gradient feature. So now I'm going to explain our proposed approach more in detail. So the proposed descriptor is an extension of the Boom descriptor that we call Spatio-Angular Binarized Orientation Maps, or SABOM in short. And the main idea is to exploit the 2D angular gradient of the light field in addition to the 2D spatial gradient. And the first step is to compute the 4D light field gradient. And for that purpose, we independently compute the 2D spatial gradient and the 2D angular gradient using the pre-width operator for both. Once the gradient is computed, as for the Boom descriptor, our descriptor is computed for a 16 by 16 patch represented here, subdivided into 4 by 4 blocks. First, we're going to see how the spatial gradient response is computed. And we consider 16 of the 4 by 4 subblocks, whose centers are shown here as blue circles. And for each of these locations, we are considering 8 spatial orientations shown here, against which we want to evaluate the gradient response. So the detailed equation to compute the gradient response that we note R is shown here in the top right. Now the idea is that we are going to binarize the gradient response R. And a naive approach would be to normalize the gradient response using a factor S and compare the normalized response against a threshold, usually small and smaller than 1, noted epsilon. And the normalization factor S would typically be the sum over the whole 16 by 16 patch of the L2 norm of the 2D spatial gradient. But we can actually improve the efficiency of this computation in several ways. First, if we look at the normalization factor, we can use an approximation of the L2 norm as a weighted sum of the infinite norm and the L1 norm, which are much faster to compute. And for the binarization step, we can also speed up the computation by rearranging the terms of the equation. So the normalization factor S is moved to the right-hand side of the inequality to avoid computing the actual division by S. And the thresholding parameter, here noted theta, is moved to the left-hand side of the inequality. And because epsilon is small and smaller than 1, theta will be big enough so that it can be approximated with an integer. And in the end, we can carry the whole computation using only integer arithmetic without any division. And because we want to avoid division, we have omitted on purpose normalization by the L1 norm of the orientation vectors when we compute R, and the normalization by alpha plus beta when computing S. So the parameter theta in the binarization step also compensate for this missing normalization. And this is why in the final equation for the binarization, we have to use two different thresholding parameters, theta 0 and theta 1. and they depend on the parity of the index of the orientation vector. As we can see that orientation vectors with an even index have an L1 norm of 1, but orientation vectors with an odd index, shown here, have an L1 norm of 2. So for the angular dimension, the equations are almost the same, except that obviously we replace the spatial gradient by the angular gradient. And the main difference is that we now consider only 8 subblocks whose center are shown as red squares here. And that we have a finer evaluation of the gradient directions by using 16 orientation vectors. And the first 8 are the same as for the spatial dimensions, and we have the additional 8 vectors shown here. And the addition of these 8 vectors means that we need an additional thresholding parameter θ2, because the L1 norm of these orientation vectors is now 3. So in the end, we can compute the angular gradient response for 8 subblocks over 16 orientation, which creates 128 bits descriptor as for the spatial descriptor. And by concatenating the spatial and angular descriptors, we obtain a unique descriptor of length 256 bits. So in addition to these algorithmic choices, there are several important implementation details to consider that we list here. And the parameters alpha and beta were found by directly minimizing the L2 norm approximation error. And the thresholding parameters theta were found by sweeping a range of values and finding the ones that give the best ROC performance for the descriptor. And you can notice that we rounded the theta values to powers of 2, which is necessary to implement the binarization with the bit shift operation. So now that we have seen in details how to compute the SABOM descriptor, I'm going to explain how it can be used in a disparity map estimation framework that we proposed a few years ago. And it's very similar to the optical flow estimation method described in the paper introduced that also introduced the BOOM descriptor. So I want to make clear that we use this framework to compare the proposed SABOM descriptor against existing descriptors. But we are aware that in itself, this framework does not necessarily produce the best performance in terms of accuracy compared to more recent work. So this is an overview of the framework. And the output of the CPM is a sparse set of matches. First, because the matches are computed on a fixed sparse grid, but also because we can eliminate matches for which the distance between descriptors is considered too high. And this is controlled by a check threshold parameter called θdesc. And the last step to obtain a dense disparity map after CPM is to apply an edge-aware guided filter on sparse matches. And for that, we used the permeability filter. So now that we have seen how to compute the proposed SABOM descriptor and how to use it for disparity estimation, I'm going to present our experimental results. So in our experiments, we use 2 synthetic datasets from the ACR benchmark and the INRIA dense dataset, which provide ground truth disparity maps, so we can compute quantitative results. And we also use the Stanford gantry dataset for quantitative results, for qualitative evaluation. So first, we want to evaluate the ROC performance of the proposed descriptor against existing descriptors. And the procedure that we used is summarized here. The main idea is to build a database of pairs of matching and non-matching light field patches. Using this procedure, we were able to generate around 200,000 patches for the INRIA dataset and around 400,000 patches for the HCI dataset. So we have enough patches for our study to be statistically relevant. Once we have constructed this database of matching and non-matching patches, we can compute the descriptors that we want to test for each patch, and then compute the distance between the descriptors for each pair of patches. Then we can threshold this distance to predict if it is a match or not, and we can sweep the range of this threshold and plot the corresponding true positive rates against the false positive rates, which gives the ROC curves that we can show here. In general, we can see that the DAISY descriptor has the best performance, and our SABOM descriptor is second best, followed by SIFT, and finally BOOM. So it's especially interesting to see that our proposed approach is outperforming the original Bloom descriptor, which confirms that it's interesting to use the angular gradient information for light fields. So then, in terms of computational complexity, we can see that in this table, our descriptor is faster to compute than DAISY and SIFT, but a bit slower than Bloom, which is the price for the improved ROC performance and is due to the additional angular gradient computation. And we can see that the advantage of the binary descriptors like Bloom and SABOM is not only that they are faster to compute, but also the distance between descriptors is much faster to compute than SIFT and DAISY. So then we compare the descriptors for disparity map estimation. And for this experiment, we only estimate the disparity map for the center view using the 3x3 surrounding views. For the CPM, we use the sparse grid spacing of 3 pixels. And then the last important parameter is the check threshold used to remove outliers. Since we use the mean squared error to evaluate the quality, in order to have a fair comparison between the descriptors, we need to have a similar density of remaining matches after the check threshold. And it's almost impossible to find a value of the check threshold for which we can obtain the exact same matching density for different descriptors. So instead, we sweep the check threshold so that the matching density roughly ranges from 0 to 100%. And then we plot the MSE against the matching density. So these are the curves we obtain for this experiment. And on top here, we have the results for the intermediate sparse disparity maps at the output of CPM. And on the bottom, we have the curves for the dense disparity map after applying the permeability filter. And we can see that the proposed SABOM is competitive with the other descriptors, and in particular, we can see that it is performing better than the Bloom descriptor, which once again confirms that it is interesting to use the angular gradient information. So in terms of computational complexity, we have similar results as before, where SABOM is not as fast as the original Bloom descriptor, but faster than SIFT and DAISY. And so we can overall conclude that the proposed SABOM descriptor offers a good trade-off between speed and accuracy. So before ending this presentation, I want to show visual examples of disparity maps, and there are a lot more of these results available on our webpage as well as the code. And don't worry if you don't have time to write down the links, you can find them in the paper. So this is an example of results obtained on light field from the Stanford dataset this time. So on the left, you can see the sparse matches obtained with CPM and the proposed SABOM descriptor. And on the right, you can see the final dense disparity map after applying the permeability filter. And now we show on the left the dense disparity map obtained with the SIFT descriptor, and visually the results are similar. But with the proposed descriptor, the computation is much faster, especially on this dataset with a higher spatial dimension. The resolution is 1024 pixels by 1024 pixels. So the disparity map computation for SIFT takes 28 seconds, but only 8 seconds for the proposed SABOM descriptor. So now we're reaching the end of this presentation, and in summary, I presented a novel binary descriptor for light field interview matching, which takes into account the angular gradient information, and our experiments show that it provides a good trade-off between speed and accuracy compared to existing descriptors. One of the limitations due to using the angular gradient is that our proposed descriptor does not perform well on sparsely sampled light fields. So in future work, we would like to address this limitation, and we also believe that our descriptor could be used to improve the performance of other disparity estimation methods or even other applications based on interview matching, such as the example cited here. And thank you very much for your attention.